Who is my neighbor? This week we're going to look at nearest neighbor networks, which have many different applications, as we'll see in this lecture. So nearest neighbor graphs are based on the choice of an integer k. We have to have some way of measuring distance or similarity, and at some point we'll need a method for avoiding bad neighbors. So in the last lecture we looked at the sub-economy problem, 250 households. In this lecture, our motivating problem is going to be the small town zoo. Zoo visitors rate animal exhibits from 1 to 5, but of course they don't rate all of them. Our first problem is that some of the ratings are corrupted. The zoo knows a household made a rating, but the result is not legible. The second one is that the zoo would like to use their data to recommend animal exhibits to households, and in particular recommend things they haven't seen, and hopefully use the data to predict things that most likely appeal. And then, of course, we'll later look at this idea of, can households be clustered? And that will be for a later lecture, but is also something that we can look at. We'll look at all three, however, with k nearest neighbor graphs. So suppose we have a numeric data set. So we have numbers everywhere. And let's suppose we define a measure of similarity between two observations. Or we could use a concept of distance. We'll actually see both. So we're going to relabel the observations. V sub k for the observations. The features are x sub l. And we're going to define a measure of similarity between two observations. And then we're going to use the observations as nodes or vertices. And once we've done that, we're going to choose a fixed number k and connect each vertex to the k vertices closest in similarity, or distance, if that's our metric. So here we have k equals 2. And you can see we end up with a k nearest neighbors graph for k equals 2 in this small example. Now, the important thing to remember is that nearness is a criteria. That is, it's a function. We'll be using the criteria, the capital K of x comma y as some number. And then we'll look at the k best values of capital K, the criteria function, in order to figure out how to hook things up. Now, there are issues. Some households may not have neighbors. They may not be close to anybody. Or there may be fewer than k neighbors. Calculating nearness is a pre-processing step, and we know what can happen with pre-processing. Proceed with caution. So what do we mean by nearness? Nearness may refer to how close two households are via some distance measure. Nearness may refer to how similar or alike two households are. Nearness also may refer to how well what the two households have in common explains each household individually. Now, this is bordering on the idea of information, which will be in the next lecture. Now, let's look at distance versus similarity. Distance, the closer the distance is to 0, the closer an observation x is to an observation y. When we use distance, a very important idea is that all the features have to have the same units. The types of distances we can look at are Euclidean, and also we'll look at absolute deviation. Similarity means that the closer k is to 1, the more that an observation x is similar to observation y. And here we're looking in particular at non-geometric types of comparisons. In particular, correlations and cosine measures will be the two that we focus on. For example, suppose we have X is ratings for 177 zoo animals. And let's suppose that we have two such observations. And so we have X is x1 to xn, where the little n is 177, and Y is y1 to yn, where little n is to 177. The Euclidean distance between these would be the sum of the squares of the differences and then that entire quantity you take the square root. And that would be our criteria, how close x is to y. The Manhattan distance is the sum of the absolute values of the differences of the x's and the y's. Now let's look at some notation. Often we use capital sigma to denote summation in order to shorten expressions involving sums. So the Manhattan distance, the sum of absolute differences, can be written in sigma notation, as you see here. The Euclidean distance, the root of the sum of squares, can be written as the square root of summation xj minus yj squared. An important principle when working with sigma notation, and I like to say it this way, when in doubt, write it out. So if I have some sum, k equals 0 to 3k plus 2 over 10 to the k, then I don't want to play games with symbols if I want to understand what that really says. Remember, you can always write it out and figure out exactly what it says. Sigma is only shorthand for summation. It shouldn't be a replacement for the concept of adding one thing to another for some long list of numbers. Let's look at some common similarity measures. One that you may already be familiar with is correlation. And here we have on top in the numerator the differences of x and x bar and y bar. And we take those and we multiply them together, and then we add them up from 1 to n. And in sigma notation, that looks like this. Cosine similarity is actually the same thing as the above, only the x bar and y bar are replaced by 0. Now, a k nearest neighbor graph is a directed graph. And a directed graph has the following properties. Each edge has a direction, and you can see in the diagram that we have edges that have arrows indicating their direction. Two edges, UV and VU, are not the same. Why? Because they have different directions. The out degree of a vertex V is the number of edges beginning at V, and the in degree is the number of edges ending at V. So in this graph, we see that the vertex V has an in degree of 3 and an out degree of 1. You'll notice the out degree of 1 corresponds to the fact that there's an edge that has both directions as indicated by the two arrows on the same edge. Now a KNN nearest neighbor graph is a directed graph in which the out degree of each vertex is k. And the k out neighbors are the k closest vertices, or the k closest observations to the given observation. And close is defined with our criteria function. So the process is that you calculate closeness among all the vertices, and then you connect each vertex to its k nearest neighbors. So let's look at some examples. So let's suppose we have some data, and here we're just looking at 7 observations, each with 4 features, and we're going to construct from this little simple example using the Euclidean metric. You'll see where our capital K is the Euclidean metric, and we can implement that with the Python command norm, and you see there the Euclidean distance between these two observations. Now we can create an entire distance matrix in the same way. And so there you see the distances, respectively, between the different vertex pairs. Now once we have that, we're going to, instead of using the matrix actually isn't convenient. What we're going to do is we're going to rewrite our information in terms of the vertex, the vertices in the edge, and the distances between them. So, in other words, we have the vertices, and then we're going to sort that So we see that from 0 to 6 is a distance of 1, from 2 to 4 a distance of 1.0. And you can see it's increasing, and here's a different view of the first three. And so this would tell us that 0 is going to be hooked to 6, 2 is going to be hooked to 4, 4 is going to be hooked to 6. And all we have to do now is iterate through the list until everybody has an out degree of k. And once everybody has an out degree of k, we have our k nearest neighbors directed graph. And in network X, that's shown the direction is in the direction of the thicker part of the edge. So let's verify that we actually did show up with a k equals 3 nearest neighbor graph. So what would we actually do with this? Well, the first problem we're going to look at is what's called imputing, or replacing missing data. So we're going to look at imputing or replacing missing data. Now we have to be careful. This is a pre-processing step, and pre-processing always introduces some bias. However, given that, to impute missing data is we simply construct the k nearest neighbors graph, ignoring the NA values in the construction, and then we infer or impute the value for an NA as the average or majority value of the same feature from its k nearest neighbors. So let's go back to the notebook. So here I have another small data set. Notice I've got some missing values marked by the NaN. And what we're going to do is we're going to see how we would actually replace those using a k nearest neighbors graph to see if we can predict what that NaN was before it got corrupted. Now every big data problem is unique. So we're going to write a little routine that's going to handle the NaNs for us because the Python norm doesn't. So for instance, look at our row 1 data and notice that when we use Pylab's norm, it returns an NaN. Why? Because it doesn't know what we're trying to do. So we wrote a norm that ignores the NaN and see that the norm of row 1, observation 1, is this 8.9. So now we use this norm ignoring NaNs, and usually we use k equals odd, or not always, and now we've got our nearest neighbor graph. Once we have our nearest neighbor graph, if we want to impute missing values, then we look at the nearest neighbors, which turns out that 8, 9, 5, 6, and 0 are the nearest neighbors to 1. So let's look at the average. So we see that the average is 0, 0.6, and therefore that 0.6, the second one, we would impute as the value to put in for the NaN, the missing value. So once we've pre-processed the data, the NaN will be replaced by the 0.6. Now this is using an averaging scheme. We could also use majority vote, or there's all sorts of different ways we could look at this. So let's look at some additional cautions and just summarize what we've said in this lecture. So k nearest neighbors can be used in pre-processing. We can infer or impute properties of a vertex from those of its neighbors. We can smooth, filter, edit, reject. And all of this comes by saying that we can do to a household or to an observation, we can infer what to do to it from its k nearest neighbors. This is pre-processing. Now, a few things to keep in mind. A k nearest neighbors graph is not necessarily a connected graph, so don't assume that we've created a connected graph. And a k nearest neighbors can also be the wrong final thing. It's very often the first thing to look at, but not always the last thing we'll be working with. We'll see that in the last video.